The Andromeda Nebula has been known to man since ancient times. The first to notice it were the Chaldean priests, astronomers of the ancient world. At some point in the past, the Andromeda Galaxy was the spitting image of our home, the Milky Way. But with the development of astronomy, this myth was dispelled. It turned out that the Milky Way and Andromeda belong to different subclasses of spiral galaxies, and the configuration of their arms is quite different. But nonetheless, they still have a lot in common. For example, an appetite for devouring their dwarf satellite galaxies. Their internal structure is also similar. The Andromeda Galaxy, also known as M31, looks like a spiral, the lines of the arms of which being evenly dispersed around the spherical bulge, the central, bright part of the galaxy, which consists mainly of old, bright stars moving in extensive, elongated orbits. The Milky Way today, on the other hand, is assumed to be a galaxy of the SBBC classification, a barred spiral galaxy. The difference between our galaxy and M31 lies precisely in the bar. This is the portion that extends from the edges of the bulge and connects it to the arms. The nucleus of the Andromeda Galaxy, like the nuclei of many other galaxies in the universe, has candidates located in them that have the potential to become supermassive black holes. Based on the results of calculations, the size of such an object could exceed that of up to 140 million times the mass of our Sun. In addition, the Hubble telescope discovered a mysterious disk which contained young blue stars surrounding supermassive black holes. They revolve around a relativistic object in exactly the same way planetary bodies do around their stars. Astronomers are a bit puzzled by how this kind of a disk could form so close to such a huge object. According to calculations, the enormous tidal forces of supermassive black holes should limit the gas and dust clouds from coalescing and forming new stars. Well, further observations will likely provide us with clues to this mystery. According to rough estimates, the Milky Way may contain between 100 and 400 billion stars. But this is nothing compared to Andromeda, which may contain about 1 trillion. Thanks to the Hubble Space Telescope, among this trillion, scientists have learned about the presence of a very large and sparse population of hot and bright stars. Hot young stars tend to appear blue. However, the blue stars found in the Andromeda Galaxy appear to be growing old, more like the Sun, stars that have burned out their inner layers and are revealing their hot blue cores. They are scattered all across the center of the galaxy and are the brightest in the ultraviolet range. Besides that, there are other interesting objects located in the core of M31. Along these lines, a double or a binary cluster of stars was discovered in the center of Andromeda Galaxy. This discovery turned out to be highly prized by the astronomical community, since the merging of the two clusters into one could happen over a fairly short period of time, roughly in about 100,000 years. Based on calculations, astronomers have determined that the merging should have happened millions of years ago. However, due to some strange and still inexplicable reasons, it did not happen. According to one hypothesis, there may not be a double cluster at all in the middle of M31, but rather something like a ring consisting of old red stars. The ring might look like two clusters, because when observing, we only see the stars from the opposite side. The ring of the disk is turned to our galaxy on one side, from which it can be concluded that there is a certain interrelation between them. When studying the center of the Andromeda Galaxy using the XMM Newton telescope, a group of astronomers also discovered 63 discrete sources with X-ray emissions. Most of them, that being 46 objects, have been identified as binary X-ray stars, whereas other objects are acting as neutron stars or candidates for black holes from binary systems. About 460 globular clusters have also been registered in the galaxy. The most massive of them, Myal-2 or G1, has a luminosity greater than that of any cluster in the local group. It is even brighter than the brightest cluster in the Milky Way, Omega Centauri. It is located at a distance of about 130,000 light-years from the center of M31 galaxy and mainly consists of about 300,000 old stars. Similarly, the PA99N2 star is located in Andromeda, around which orbits the exoplanet, which is the first to be discovered outside the Milky Way. But as it stands today, the planet is still considered to be unconfirmed. However, in view of the scale of the Andromeda system, the presence of so many stars in it, and an even larger number of planets, it is quite possible, at least according to the logic of the theory of probability, that among this abundance of planets, there are planets that are quite suitable for life, or already have life on them. After hundreds of thousands of years, we will be able to see everything much better, given the fact that a collision of the Andromeda galaxy and the Milky Way is inevitable. Mind you, this will happen in about 4 billion years. We'll be substantially older. Well, we tried to put together all the most interesting facts about our celestial neighbor. If you want to find the Andromeda galaxy in the night sky, then the best time to observe it is the autumn and the winter. In a dark sky out of town, it will be visible to the naked eye. What's interesting is that because of the finite speed of light, we are seeing this object as it was 2.5 million years ago. Shall we say 2.5 million years ago on Earth, there were no representatives yet of the modern human species. Unfortunately, according to the theory of special relativity, there is no way to know what this galaxy looks like at the present moment, given that what we see is for us the present moment. At some point, every single one of you has contemplated the thought, what is infinity anyhow? How can you understand it? How can you imagine it? How can you wrap your mind around it? And how can you picture an endless sequence of numbers? A constant which never ends. A number that includes the phone numbers of all your acquaintances, the dates of birth of all the people on the planet, their credit card numbers, the designations of all known stars, and even the date of your dentist appointment. All of this massive series of numbers is contained in an amazing mathematical constant, the number pi. And despite the fact that it has been known since ancient times, to this day, pi stimulates the minds not only of scientists, but also of ordinary people. Those who first calculated the number pi can be considered prehistoric people, who, when weaving baskets, noticed that in order to get the desired diameter, it was necessary to use a reed 3 times as long as the diameter. This fact was recorded on tablets made of baked clay that were found in Mesopotamia. Examples of accurate and not entirely accurate calculations of the number pi can be found in the works of Egyptian, Babylonian, Indian, Chinese, and ancient Greek geometers. So what is this mysterious number pi anyway? It is a mathematical constant that expresses the ratio of the circumference of a circle to its diameter. Many ancient scientists, including Archimedes, try to calculate pi each time by filling a circle with polygons that had an enormous number of sides, so they would more tightly fit within the area of the circle. Archimedes used a 96 gun. Chinese mathematicians fit in a 192 gun, then a 3072 gun, and finally they managed to fit a polygon with a 24,576 sides into a circle. This is why many mathematicians contend that a circle is a figure with an infinite number of angles. Up until the 15th century, only 9 decimal places were known. Isaac Newton calculated the number pi to 16 digits. As recently as the 19th century, it was calculated out of 707 decimal places. But with the advent of computers, this process has accelerated significantly, and now science has already identified about 50 trillion decimal places. Pi is irrational. Its decimal representation never comes to an end, and it is not periodic. Consequently, based upon the formula that the circumference of a circle is equal to pi times its diameter, the circle doesn't come to a close, since there is no finite number. This fact can also be closely related to the spiral characteristics in our lives. After all, even the orbit of our Earth is not at all a circle. It moves in a spiral relative to the center of the universe and space-time. A logical question arises. How many numbers do you need to know in order to make a given calculation? Let's round pi up to the 15th digit. And as an example, let's take the farthest spacecraft from the Earth, Voyager 1, which is located at a distance of about 20 billion kilometers. Imagine a circle with a radius this size, in other words, a diameter of 40 billion kilometers, for which we want to calculate its circumference using formula 2 pi r. It turns out to be a little more than 125 billion kilometers. We don't need to put emphasis on the exact circumference. We are interested in the error of the measurement. So it turns out that the circumference using the constant rounded up to 15 digits is calculated with an error of less than 4 centimeters. Think about that. We have a circumference of 125 billion kilometers, and the margin of error is less than the length of your little finger. We can study the problem using the example of the Earth. The diameter at the equator is 12,756 kilometers. The circumference of the equator is 40,075 kilometers. which is the distance you'd have to cover if you want to travel around the world, not taking into account mountains, valleys, and obstacles like buildings, parking lots, ocean waves, etc. How wrong is your odometer when using a rounded-off value of pi? Its error is about the size of a molecule. Naturally, there are different kinds of molecules which do differ in size, but you get the idea. The size of the error is about 10,000 times less than the thickness of a strand of hair. Now, let's take the largest possible object, the visible universe. Its radius is approximately 46 billion light-years. How many decimal places of pi do you need to use to calculate the circumference of the universe with an error of no more than the diameter of a hydrogen atom, the smallest atom? You need 39 places following the decimal. If you think about how huge the universe is, well, and truly larger than we could ever comprehend, and such a tiny atom of hydrogen, you will then understand that a really accurate calculation doesn't require very many decimal places of pi. There is an abundance of surprising facts about this constant. Stanislav Ulam, a Polish-American mathematician, in 1965 wrote the numbers of pi out on graph paper. He put the 3 in the center and, moving in a counterclockwise spiral, wrote down the numbers after the decimal point. In addition, he drew circles around all the prime numbers. He was both surprised and aghast when he noticed that the circles were organized in straight lines. Then, using a special algorithm, the mathematician made a color picture based on this drawing, which is called the Ulam spiral. Seeing that pi correlates a curved object, a circle, with a straight object, the diameter, we can find it in all sorts of places. Some find the number pi in riverbeds, the length of a river with all of its meandering bands in relation to the straight line between its source and its delta, according to calculations, is on average pi. Models for virtually all wave-related phenomena will involve the number pi. Let's take light and sound, for example. Pi determines what colors are visible in the spectrum of a rainbow and how the note C should sound. The number pi is also observed in the process of the cells in apples acquiring a spherical form and in the brightness of the light output of a supernova. Well, perhaps the code of the universe is encrypted in this number. One of the moons of Jupiter, known as Io, played a significant role in the advancement of 17th century astronomy. Studies had shown that in the process of crustal compression, about 100 mountains were formed on the surface, changing the landscape over the next number of centuries. The peaks of some of these, for example South Busal Mons, exceed the height of Mount Everest twice over. Along these same lines, there are vast plains on the surface of this satellite. Its surface has unique properties and comprises an abundance of colors: white, red, black, green, and even orange. This distinctive characteristic is due to regular lava flows, which can stretch up to 500 kilometers. The high density indicates that there is virtually no water on this satellite, although there have been small pockets of water accumulation found. This deficiency of water is likely due to the fact that during the formation of the solar system, Jupiter was hot enough for volatile substances such as water to evaporate from Io's surrounding vicinity, although not hot enough for this to happen on the more distant satellites. Correspondingly, often found on the satellite's surface are volcanic depressions, just like in humans, although they are called paterae. They are characterized by an even floor and steep walls. They very much resemble terrestrial calderas. However, it is still unknown whether they were formed by the collapse of the magma chamber and the collapse of the top of the volcano, like their terrestrial counterparts. Unlike similar geostructures on Earth and Mars, volcanic depressions on Io generally do not lie on top of shield volcanoes and are usually larger, with an average diameter of about 41 kilometers, and the largest, Loki Patera, is 202 kilometers in diameter. It is remarkable, but paterae often serve as sources of volcanic eruptions or far-spreading lava flows, as in the case of an eruption in the Gishbar Patera, or they themselves fill with lava, becoming lava lakes. The lava lakes on Io are covered by a lava crust which crumbles away and renews continuously. Image analysis has shown that the lava flows on Io are primarily composed of molten sulfur. However, subsequent ground-based infrared observations indicate that the flows are, in fact, composed mainly of basaltic lava and ultra-basic rock. An outstanding representative is Masubi, an active volcano on this moon of Jupiter, which is located on Io's leading hemisphere, in the Taurus region. The volcano is noteworthy for one of the largest lava flows, both on Io and in the entire solar system, covering an area of 240 kilometers. Despite the extensive volcanism that characterizes Io's appearance, most of its mountains are not volcanic in origin. The majority of them are formed as a result of compressive stresses in the lithosphere, which lift and often tilt portions of the satellite's crust, thrusting them over each other, much like giant ice flows. This is precisely why virtually all of the mountains of Io are at some stage of destruction, with large landslides being widespread at their bases. It appears that cave-ins are the main factor in the destruction of mountains. Believe it or not, but this tiny cheese ball, Io, plays an important role in shaping the magnetic field of the giant planet Jupiter. The magnetosphere of Jupiter absorbs gases and dust from the thin atmosphere of the satellite with a speed of 1 ton per second. All this matter, depending on its composition and degree of ionization, ends up in the various neutral clouds and radiation belts of Jupiter's magnetosphere, and sometimes even escapes Jupiter's system altogether. Also interesting is the fact that Io's moon is surrounded by a so-called atomic cloud of sulfur, oxygen, sodium, and potassium, which extends to a distance from its surface equal to about 6 times its radius. These particles come from the upper atmosphere of the satellite, and they are activated by collisions with particles from the plasmators and other processes in Io's heliosphere, where its gravitational strength exceeds that of Jupiter's. Io's orbit runs its course within the radiation belt, known as the plasma torus, a donut-shaped ring of ionized sulfur, oxygen, sodium, and chlorine. The plasma in it is formed from the neutral atoms of the cloud surrounding Io, which is ionized and carried away by Jupiter's magnetosphere. It's not hard to guess that Io is not at all like most satellites of the gas planets, which contain huge masses of ice, as it consists mainly of silicates and iron, like the inner planets. Further still, its interior is also incredibly active. Modeling of Io's internal composition shows that at least 75% of the mantle consists of the magnesium-rich mineral forsterite, a composition similar to that of L-chondrite meteorites. It is obvious that the ratio of the concentrations of iron and silicon there is higher than those on the Moon or the Earth, but lower than on Mars. The latest research has shown the presence of an induced magnetic field on Io, for which an ocean of magma with a depth of 50 kilometers would be required. This layer is estimated to be 48 kilometers thick. It makes about 10% of Io's mantle, and its temperature reaches about 1200 degrees Celsius. It is not known whether this 15% melting is compatible with the conditions of significant amounts of molten silicates in this inconceivable ocean of magma. Io is a bright and wondrous world, which has no equivalent in the entire solar system. Active volcanism on a satellite the size of our Moon is absolutely astounding, and the pioneering photographs of the satellite surface, which have been obtained by a number of spacecraft, compel us to plunge again and again into the atmosphere of this distant and mysterious world. Amazing outer space and the remarkable beauty of the galaxies to which there is no end or brink. We invite you to become acquainted with the closest of them and to explore their unique features, which are capable of capturing our imagination and are of particular interest to astronomy. Now then, the local group of galaxies, like its other neighboring groups of galaxies and more densely populated clusters of galaxies, is part of a mass concentration, the local supercluster of galaxies. This system has a diameter of about 100 million light-years and a thickness of about 35. Its center is a massive cluster of galaxies in Virgo, separated from us by a distance of 50 million light-years. And the first to take this galactic baton is the third largest galaxy in size and mass in the local group, as well as being the closest unbarred spiral galaxy to the Milky Way. This refers to M33, or the Triangulum galaxy in the constellation of the same name. It possesses the enormous black hole X7, which has a mass equal to about 16 times that of the Sun. It is one of the largest known stellar mass black holes. In addition to the Milky Way and its satellites, the Andromeda galaxy, the closest giant spiral-type barred galaxy to us, also with its satellites, which dominates the local group, also belongs to a friendly company of galaxies which stretch out for about 3 million light-years in width. It is separated from us by a distance of 2.5 billion light-years. It rightfully occupies a dominant position, since it is 1.5 times more massive than our galaxy. But we will not dwell on it in greater detail, since the channel already has a separate video completely dedicated to this world. We continue our journey, and before us stretches galaxy NGC 5128, or Centaurus A, the closest lenticular galaxy with a polar ring to the Milky Way in the constellation of Centaurus. This is one of the brightest and closest to us of the neighboring galaxies. In terms of brightness, this galaxy ranks 5th after the Magellanic Clouds, the Andromeda Nebula, and the Triangulum galaxy. Before us is the irregular Wolf Landmark Mallet galaxy, discovered in 1909 by Max Wolf. It is located in the constellation of Cetus, at the edge of the local group. It's at a distance from us of about 3 million light-years, experiencing tidal interaction from another member of the local group, the dwarf elliptical galaxy PGC 29194. Further is NGC 300, a spiral galaxy from a group of galaxies in the Sculptor constellation. This is the closest cluster of galaxies to us. It is located about 6.1 million light-years from the Milky Way. Astronomers have ascertained that NGC 300 is larger than had been previously thought. It turns out that the galaxy belongs to a large rarefied outer disk of old stars, more than twice the size of any known before. Thus, the size of NGC 300 turned out to be 47,000 light-years. We continue our journey, and we see in front of us galaxy NGC 55, a galaxy in the southern hemisphere of the sky, located on the border of the Sculptor and Phoenix constellations, seen almost edge-on. NGC 55 is an SBM, barred Magellanic Spiral type dwarf galaxy, and is relatively close, at a distance of 6.5 million light-years. In the visible range, 4 concentrations with increased brightness can be noted, which are the largest globular clusters. The galactic nucleus is the most powerful radio source in the constellation. It belongs to the Sculptor group of galaxies, where it is one of the largest. But in order to reach the galaxy Maffei 2, you'd have to grow older over and over and over again, since the galaxy is located at a distance of 12 million light-years. Maffei 2 is a spiral galaxy located in the constellation of Cassiopeia. Most of the galaxy's infrared radiation comes from cosmic dust. This dust is found primarily within the spiral arms and has been shown to be associated with star formation. (404). No, this isn't a fault in the matrix. It's the name of the next galaxy in front of you, the NGC 404 galaxy in the constellation of Andromeda. Due to its proximity to the bright star Mirage, which obstructs observation of NGC 404, the galaxy is called the Ghost of Mirage. The galaxy and the star are approximately 7 minutes of arc apart. Thanks to this sort of neighborhood, the Ghost of Mirage is easy to find even with a small telescope. You just have to locate Mirage, and the galaxy will also be in the field of view. Further is NGC 2403, a galaxy in the constellation of the Giraffe, part of the M81 group of galaxies. Most of the stars that populate this galaxy are old metal-poor stars, about 12 billion years old, which arose in the early burst of star formation. But there are small groups of young, hot, blue stars. Galaxy NGC 2403 is part of the M81 group of galaxies. Visibly, the galaxy also contains blue open clusters, dark dust streaks, and a relatively small core glowing in the center. In addition to NGC 2403, the group also includes another 40 dwarf galaxies. We're arriving at the next incredible object, the Cigar Spiral Galaxy, or M82, in the constellation of Ursa Major. This is an object with fairly powerful star formation and a supermassive black hole in the center, with a mass of as much as 30 million solar masses. Yet another amazing galaxy, PGC 45279, is a barred spiral galaxy SBC in the constellation of Centaurus. It looks quite similar to our galaxy, but X-ray observations show the presence of a Seyfert quasar-like nuclei, probably containing an active supermassive black hole, and it's at a distance to us of 11.7 million light-years. And finally, the most distant object that we will get a view of today is the Caldwell Galaxy, Caldwell 5 or IC342, an intermediate-type spiral galaxy in the constellation of Giraffe. It is located near the galactic plane, where the absorption of radiation by dust hampers observation of the galaxy. For the same reason, it is difficult to determine the exact distance to the galaxy. Current estimates place it at a distance of 17 million light-years. That wraps it up. Our short journey observing the most interesting galaxies in the local group has come to an end. The study of these objects is very useful and instructive for explaining the formation and history of the life of the most commonplace, the most abundant star systems in the universe. When we speak of the spatial extent of the universe, it is necessary to separate two concepts. The first is the size of the observable portion of the universe, or the span of the current horizon. The name speaks for itself. It is the direct equivalent of the horizon as we define it on Earth, the imaginary border of the visible part of the Earth, and in this case, the universe. We don't see whatever lies beyond this border. That's not necessarily because there is nothing there. Just as in the case of the Earth's horizon, we don't see what is beyond because the light from there hasn't reached us. When it comes to the Earth's horizon, it doesn't reach us because the Earth's surface obstructs it. In the case of the cosmological horizon, the light from the photons simply hadn't had enough time to reach us. The unique thing about observing distant objects in space is that the light registered from these objects today has traveled throughout the universe for a long time, and in actual fact was emitted an extremely long time ago. Thus, objects located at cosmologically large distances are objects that have existed since the beginning of time and emitted the light that we register very, very early on. The very earliest signal of which we are aware and have studied well is the extraordinary cosmic microwave background radiation, which appeared in the era of hydrogen formation, when there were no galaxies or stars. At that distant time, the universe was 1 billion times denser, and photons were 1,000 times hotter than they are today. As these photons spread throughout the universe, it was expanding. By reviewing microwave research, information can be obtained about the characteristics of the expansion of the universe, its composition, and internal structure. The most distant region that is possible to see and distinguish is the last scattering surface. It is from there that the cosmic microwave background photons emanate. This is the so-called surface of the last scattering. Beyond this region is what is not yet subject to study by our devices. We cannot see the area that is located beyond the surface of the last scattering because it is opaque. After all, it is light that allows us to see distant objects and judge their properties by one means or another. Regardless of the fact that it is impossible to see what is happening beyond the last scattering surface, researchers are able to form an opinion about the expanse beyond it. To do this, they observe what effect it has on existing astrophysical objects. More than that, according to the latest data, galaxies are moving away from each other at an accelerated pace. And the further away the galaxy is, the faster it is moving away from us. This means that at some point the speed of the separating galaxies will exceed the speed of light, and we will no longer see them. These objects will go beyond the horizon, but will not disappear. This fact implies that perhaps out there, beyond the observable universe, lies an additional vast expanse that is hidden from us by the barrier of the speed of light. The point being that CMB maps made with telescopes such as those of NASA's WMAP and the ESA's Planck showed on a vast scale a mystifying lack of perturbations. This jaunty little word means the departure of a celestial body from an orbit because of the influences of forces other than the gravitational attraction of the center of mass of the system, such as other celestial bodies or environmental resistance. In order to find out if these missing perturbations could be caused by a multiply connected universe, scientists made many computer simulations of what the cosmic microwave background radiation would look like if the universe had the form of a giant three-dimensional donut, where it is connected to itself in all 3 dimensions. The properties of the observed fluctuations, such as the deviation from the mean value of a random magnitude characterizing a system of a large number of chaotically interacting particles, of the cosmic microwave background radiation, show insufficient power on a scale exceeding the size of the universe. This lack of power means that fluctuations in the cosmic microwave background radiation are not present on such scales, and that our universe is multiply connected and finite. In other words, it looks like the cosmic microwave background is missing signals which must be present if the universe were truly infinite. One explanation for this suggests that the topology of the universe is curved in such a way that it connects back to itself like a donut or a bagel of intergalactic dimensions. Just as you can roll a sheet of paper into a tube without changing its parallel properties, the universe can be donut-shaped while remaining flat. This is exactly what the researchers have found out with the aid of simulations of the cosmic microwave background. It turns out that compared to the standard cosmological model, which is considered infinite, we found a much better matching observation of the fluctuations. Such a universe must have an end, and the entirety of the vast expanse is possibly no more than 4 times larger than the boundaries of the universe that is observable by man, and its size is 47 billion light-years in diameter. The universe can be self-contained in 3 dimensions and have the shape of a 3-dimensional donut. Models of the finite universe may be intimidating to some people, but you will not perceive these boundaries. For all practical purposes, you simply live in an infinite universe, despite it having finite dimensions. But even if you don't necessarily end up finding yourself at the edge of this finite universe, would you be able to circumnavigate it and return to where you started? In theory, yes. After all, light can travel across the entire finite universe. I wonder how our donut-shaped universe looks from the side, presumably situated with others. The name Earth exists in most languages, associating our planet with the terra firma, which is how we usually think of it, whereas the real and true name of our planet you can rest assured might easily be ocean. After all, liquid water in the form of hydrosphere covers about 71% of the Earth's surface, or about 361 million square kilometers, leaving only 29% of the planet's area for dry land. There are places in space from which that's exactly how our planet looks, like it's nothing but ocean, the pearl in our solar system. When we try to look beyond its bounds, we find that we are surrounded by countless rocky and lifeless planets, in actual fact, dead worlds. And finding an ocean planet is an incredible rarity. Yet ocean planets exist in other distant systems, and every so often, very rarely, we find them. But never before 3 ocean planets in one system. Even the system in which you and I are located can't afford this luxury. Welcome to an extraordinary environment, L9859, in the center of which is located a bright dwarf star of the M3V type, situated 34.6 light-years away in the southern Valens constellation, also known as TOI 175. The star is equal to about 1/3 of the Sun's mass. It is indeed a dwarf, but apparently without active flares. Consequently, that has a favorable effect upon the planets, of which there are as many as 5 in the system. The planets L9859b, C, D, E, and F. 2 of them are rocky planets, such as Earth and Venus, which are close enough to the star to actually have a chance for primitive life. But the other 3 planets may contain water below the surface or in the atmosphere. 2 of them contain a small amount of water, while up to 30% of the 3rd planet's mass can be little more than water, which makes it an ocean world. What is known about these worlds? What are the chances that they have life? This is what we will talk about, but first things first, in order. Observations were carried out using the telescopes of the VLT facility, the TESS telescope, and the HARPS spectrograph. The radii of those closest to the star, the exoplanets L9859b and C, according to TESS, range from 0.8 to 1.6 that of the Earth. These are very intriguing numbers, since a planet the size of ours is unlikely to be composed of ice or gas. Most likely, it will be similar in chemical composition to the Earth and Earth-like worlds, which for obvious reasons are of greater interest to mankind than any others. Having estimated the mass of the worlds of the L9859 system with the knowledge of their size, astronomers calculated their density. Planet L9859b is like Venus, but L9859c is almost like the Earth. It is believed that both of the exoplanets are Earth-like worlds, with small 12 to 14% of their mass iron cores. For comparison, the mass of the Earth's core is approximately 30%. Indeed, these 2 planets are interesting, but they are rocky and extremely hot for a comfortable existence. Quite another matter is L9859d, the 3rd planet in terms of distance, which is located in the middle of the system and is in the habitable zone. This world could aptly be called not the planet Earth, but the planet Water. Judging by its density, water makes up to 36% of the mass of the celestial body. This is an extraordinarily good result. During a migration due to powerful turbulent disturbances, this sort of an icy planet, with a mass of 6 to 8 times that of the Earth, can find itself sufficiently near enough to its star for the outer ice crust of the planet to melt and the planet to end up being completely covered by an ocean of liquid water as much as 133 kilometers deep. The pressure on the floor of an ocean like that would be on the order of approximately 20,000 atm, which is sufficient for the formation of polymorphic modifications of ice, which are heavier than liquid water, and under this kind of pressure will never melt. Of course, for the emergence of biological life similar to that of the Earth, it is essential that the planet be in the habitable zone. This would permit the ice layer on the surface to melt. In addition to that, crucial minerals exist in the planetary crust. Between the layer of liquid water and the crust, this type of planet has a thick layer of solid ice, blocking access to the minerals. The latter, however, can be brought in by meteorites and comets. Who knows? Maybe this planet is already teeming with marine life. Yes, of course, they will look different, since the red dwarf star has its own influence on its surrounding world. And by far, not every creature can adapt. But the truth is that we know very little about it at all. In any case, this world is extraordinarily enchanting. And what can be said about the two outermost planets, E and F? Although the data suggests, at very least, a water-rich atmosphere on their surfaces, nonetheless, these Venus-sized planets may be covered in ice and a thick atmosphere. This is also a good indicator. More time is needed to investigate these objects. But we also have good news. The largest infrared space telescope, the James Webb, is due to be launched as soon as in October 2021. And by the way, star L9859 will make its way into that zone of the sky, which Webb will be observing 200 days a year. And it is planned that in 2027, the ground-based optical telescope ELT will be commissioned, which will be 2.5 times larger than the current record holder, the VLT. By means of these instruments, it will be possible to thoroughly research the planets of the L9859 system and examine these worlds closer. Of course, we're not destined to see exo-whales from such a distance. However, it is quite possible to determine whether the planets have an atmosphere and of which gases they consist. And this is an unbelievably immense amount of data about these distant and unknown worlds.